will begin to transition into I would say logical operation, basically dealing with binary now that we know how to represent data, right, in a different format. And to do this, let me kind of quickly tell you what's the plan this week. So you, I think you should have seen the announcement already. I discovered that this Thursday is not the listed holiday on MUIC, so I think it means that I can have the class as usual. If you absolutely cannot make it, let me know. But I'm gonna record the session. If that's the case, then please make sure you send questions that you want to ask ahead of time so I can go over these questions. The class will be recorded. It will focus on the review for your quiz. If the quiz is coming up, I will post the sample exam right after this lecture. Basically, right after this lecture, you will see a file get uploaded and announcements being made that, hey, I have the sample exam up. If you're curious, please check it out. My recommendation is you should go through this sample exam so that you can come with question on Thursday. You can come with question on Thursday. All right. And here are the logistics. The repeat of the last lecture. Our quiz will be released around 9 a.m. on Tuesday, October 26th. And, well, we have a holiday 21st. And we just found until now that, okay, we can have class. But anyway, we announced the date of the quiz anyway. So it's going to be Tuesday, October 26th. You will have until Friday. That's 3.5 days. 3.5 days to work on the exam that's intended for 2 to 3 hours. All right. Don't get scared about the time I'm giving you. It's gonna be the same length or shorter. It's gonna be the same length or shorter than the sample exam that you will see. But you're gonna get a lot more time. So time management is important because you're gonna have to juggle between this, between assignment 2, and one more thing about assignment 2. So here's the deal. I already talked about section 1 and everyone agrees. So if you don't agree with this, let me know. But here's what we're gonna do for assignment 2. Oops, pen, right? I'm gonna push the deadline by 1 week. Is it okay? Anyone object to that? Anyone have any problem with that? We all get 1 more week. But if you can submit by the original deadline, you get 10% extra credit. Basically, whatever score that you get at the end, everything will be added by 10% of the grade that you got for the assignment 2. So let's say assignment 2, you got 91. 10% of 91 is 9. You're gonna get full credit. All right. So here's the deal. I'm gonna extend the open until by 1 week, right? In Canvas, I can change that. The due date will be on the same day. The due date is on the same day. So I can have the flag that say, okay, you submit by the extra credit deadline. The open until is the last day you can submit assignment 2. Already with the extra day added. So don't submit after that. All right. Don't submit after that. But I think this will give everyone more time. I also hope this would give you all the time that you might need to absorb the material and to try out why do I get sec fault. And in this assignment will be the one assignment that you're gonna have the question, why do I have sec fault? So what's the downside of this? The one downside of this is I'm gonna release this assignment. With the same schedule, right? Which means that assignment 2 and 3 will overlap a little bit. It will overlap a little bit. Make sure when it's released, take a look at that because assignment 3, the difference is it'd be less on the syntax and C part. It'd be more on is a assignment three is a puzzle. If you think about it that way, we ask about the thing we're gonna learn today, logical operation, and how to replace the common math operation on common operations with logical operation to make your program a lot faster. To make your program a lot faster. These techniques are used in compiler. That's how some of the tricks we learn GCC when you compile the code, these are being applied. So these are the techniques that computer system apply to make your code faster. These are also techniques that we, as in myself, the people who build hardware, right, apply to make your program faster. So assignment three will be released with the same schedule. Please be aware of that and be aware of the deadline because it's really, really sad when you did not realize the deadline is like in the next 2 days, right? Any questions so far? Will the quiz be mostly coding or mostly knowledge stuff? I will try my best to be the second part and less of the coding part, but it will be more. I'll try to make sure it doesn't really like, oh, okay, you can Google and you find the answer. It'll be more knowledge and applying what you learn, right? So be careful when you read the questions and make sure you understand the question before you attempt and answer that. I don't I don't think it will be hard. It might involve some coding, but the coding part I'll try to limit so that you can basically answer on the paper. And you don't have to like go open up the problem that I have in the previous semester is when I have a coding questions, it does take a little bit too much time because you have to fire up your editor and test the code, right? This time I probably will more or less have this will be more of the fill in the blank kind of format, but you might see coding. You might see coding. All right, is that fair game? So it'll be not like assignment kind of thing, but it'll be more, okay, do you know this? Do you know that? Okay, so let's start the lecture material by quickly recap what we went over last week, right? So last week we talked about what is the data word? And the way I would compare data word is I would compare that to how we use word to communicate, right? When I say, hey, my cat is actually gone. Where is he? He was here like 2 minutes ago. Basically, if I say that, right, you know that, hey, something happened, certain thing happened. The furry animal is not in my vicinity that I can look around and see, oh, okay, that's my cat. If I say the word cat, right? If I say the word cat, you know, is a type of animal that try to plot your murder at night and ask for food in the morning, right? That's the definition of a cat. And this is a convenient way for me to convey meaning to you. And that same concept apply to computer, right? A data word is a group, a unit of data where the computer would typically send from one component to another, from one function to another in this kind of granularity. It doesn't send bit by bit, but it in the physical sense, it does send bit by bit. But when you're looking at the computer programs, you are handling the data in more to the word granularity, right? So the 64-bit machine, for example, the Apple MacBook that you saw last night, they use 64 bits technology, right? So that's the Intel x86 and ARM, many of the ARM processor, as well as the AMD chips, right? 64-bit machine that use 8-byte words means that one word consists of 8 bytes. Is a unit that a hardware used to transfer the data in a single unit at a time together. But different hardware, if you look at the new types of computer, now you can control half word, for example, or just a few bytes or even 1 byte at a time. Sometimes the computer also group multiple words together. So when I said a word and the size of the word, you would go and look at the machine definition and would tell you what's in the word. And once you have that, it kind of governs how the computer put the data in the main memory, because then the next concept is bytes in a word. Because one word can maintain multiple bytes, right? So the bytes in the word can be ordered across different types of processor or architecture. Uh, Big Endian machine, the highest address, big highest, right? The highest address would be the least significant bytes. The little Endian machine, the lowest address is the least significant bytes. And some architectures support both. You just have to configure and you know where your data is. And this is basically useful when you are working with embedded processor, microcontroller. Basically, whenever you have to deal with these small chips that you programmed and you put it next to a bunch of sensors that you use in, for example, IoT situation or drones or maybe a self-driving car, right? You would know where is my data. Do I go read the byte number 12, byte number 13? How is word being organized? Is it little endian or is that big endian? Then we transition into the concept of, okay, how do I represent my data? Because everything in a computer is about data, and they only have the only one option that they can represent data is binary format, right? So let's say we can represent number in binary to represent a character, an English character, or a string, which is a bunch of characters put together, right? So each character is in the ASCII format. And to tell the end of the string, you would put null value that would determine the end of your string. So let me ask you this question. Let's say I have a string called S. What's the size of this array? How many bytes is in the array S? Can someone tell me how many bytes is S? Wait, it's a character, so it's 2 bytes, right? 3 bytes, my bad. There are three spots that I can put things in as, and each spot is 1 byte. So this is 3 bytes. Because it's a character, my bad. If it's 12, that's an array of integer, right? So if it's an array of character, there are 3 spots. This takes 3 bytes. So let me ask you this. What will happen if I want to store the string ABC in S? Can someone tell me what will happen if I store ABC in S and I say printf? So why? Well, sometime it might print actually. So that's a great example. Actually, I got an email from one of the students here, and I basically thank you for that. It's an awesome example, and it's great that you asked me this question. Right? The question is awesome, actually. So the question is, I have a string that has 3 spots, right? The question is, I want to put the letter ABC in there and I print it out. And the result of the print is basically ABC. And what I saw on the monitor was I have the hard sign at the end, and that's it. So can someone here making a guess on, well, what happened? Why does suddenly your computer declare a love relationship to you? Why does it suddenly declare a love to you? The now got replaced, right? So the first thing that happened is if you have a string that only has 3 bytes wide, how many character can you store? How many character can you store? 2 character. So let's say if I store 3 character, there's no space for the null character, right? And printf would go and read the array until it see the null character. So what it does is it would first read the first character, A, yay, I printed out. Read the second character, the next address, B, okay, I printed out. I print C, which is another letter you just put on the string, yeah, I'm gonna print it out. Have you seen null character yet at that point? No, right? So what would printf do? Printf say, okay, that's not the end of my string, I'm gonna keep reading. So it would keep reading to the next character. In this case, it is not owned by S anymore. But we'll talk about why is that still getting print. There's another reason for that. But it will print, go look at the next number. It just happened to be some random number in the memory. And that random number just happened to map to this hard symbol, right? So it print that. And we go basically read the next number, and the next number happened to be 0. So printf say, okay, that's the end of my string. That's gonna stop. It's gonna stop printing, and you see this, right? Any questions so far about what's happening here? So, great question. Great question. So the question on the chat say, hey, isn't this basically entering the area in the memory that someone else owns, right? Doesn't this require some permission check? It also happens to be if you have the memory access, the way permission works in the operating system, they would track the permission in what we call the page granularity. One page is 4 kilobytes. One page is 4 kilobytes. So toward the end of this semester, we'll cover these topics. Don't worry about that. We'll definitely cover these things. But fun fact for now, the permission is done page by page by page. So you have page 1 that's 4 kilobytes, another page that's 4 kilobytes. This is app A, this is app B, right? So let's say the string S is somewhere in here. And then I suddenly access the next address. Is that okay? Is that going to be within the application A's address space? I don't want to use that word yet because we haven't defined it. But is there a region that A can access? It's gonna keep printing, and there are two options that can happen. It will eventually find 0 and stop. So you see text and a bunch of junk until until printf finds 0. The second thing that can happen, it will keep printing until it walk over someone else's data that are in the different page. So it can keep printing until you walk in here and say, hey, I'm trying to print application B's data. That case, the OS would trigger, comes in, basically OS comes in like, hey, wait, you did not own that page. You did not own that page. So I'm gonna raise segmentation fault. All right. So the reason why it's printing without raising segmentation fault is because it's still within the same page. So the OS, because it tracks information in the page granularity. So it have no idea what's going on inside the page, right? Uh, it would allow you to print because, I mean, technically you own that page. Because you use the first 3 bytes, you own the rest of it. Malloc can give the rest if you want to allocate the memory, that's fine. That's another totally different topic already on how malloc manage the memory, which we will cover later. But when malloc is like, okay, fine, your data, your problem, right? So does it basically answer your question about isn't this entering another application's address, and wouldn't that be a segfault? So if it's still in the same 4 kilobyte range, it OS doesn't know. So the OS have no idea is that gonna segfault or not. So it would keep printing until it finds 0. But if it happened to go across and go to someone else's data, that's when it's gonna segfault, right? So is it more clear now? Okay, cool. So if you still have questions, feel free to ask on the chat. I'll go ahead, and if there's more question on the chat, I'll address that. All right. And we also cover how do we represent an integer, right? And basically we reach the conclusion that we can use binary value for that. We then determine how many bytes doesn't require to represent a number. That depends on what do you want for the maximum as well as the minimum range of the number, right? Important thing is across different version of C, the size of these things changes. Integer these days are 4 bytes, not 2 bytes. So you will have to check, right, the size of the number, right? You have signed and unsigned as well. So integer can be positive or negative. And when you say unsigned, these are only the positive number. If it's a signed number, it's represented in the 2 complements format, where the most significant bits is the negative value, the rest are the positive value, and the result is the addition of the negative plus the positive value. If you want to explicitly say, hey, treat this as an unsigned number, because by default, the number you type in is signed. So you put in the letter uppercase U to suggest to see that, hey, that's an unsigned number. We also have floating. We also cover floating point, which break things into 3 pieces. The first bit is the signed bit. The next set of bits are the exponent bits, and the mantissa bits are whatever comes next, right? So the typical 32-bit floating point format is you have 8 bits for the exponent, 23 bits 23 bits for the mantissa, and 1 bit for the signed bits. The equation is basically follow this. You use the exponent minus 127 and raise that to the 2 to the that number, multiply by the mantissa bits, and multiply by the signed bits. All right. These floating point format is used a lot, and it's used everywhere, right? And you can have different size for the floating point as well. Anyone hear about this format called double? So double basically is a larger floating point. It covers larger range, has bigger exponent bits, bigger mantissa bits, which means that it is wider. How about this format called TensorFloat32? Anyone hear about this? So this is probably something that you might not have heard about it. But if you program on the GPU, the newest model on the GPU say, hey, I support this format. This format is actually not a 32-bit floating point, it's 19 bits. Is this 19? I think it's 19 bits or 18 bits. If I don't remember the exact number, to be honest, but I think it's less than 20 bits. The only difference between the typical 32-bit floating point is TF32 has 1 sign bit, 8 exponent bit, and fewer mantissa bit. So what's the difference here? The range that the number can cover is the same as floating points. But the GPU, let's say I work on deep learning. Anyone hear about deep learning or machine learning? or like heard about this word, right? So in machine learning, it's quite you had a fun project with this. Uh, so it's quite common to basically reduce the accuracy. This is fine. You can make the number smaller. I mean, not smaller, but like have lower precision. You don't have to have the same accuracy, and you can still train or finding the answer when you want to do inference. Inference is when you have the model, you want to use the machine learning model to predict something, right? So you can use TF32, which has lower accuracy to represent your data, and that way you have better performance, right? So the format of the floating point, the key here, the main key point is there are three pieces of information: sign bit, exponent bits, mantissa bits. The rest they work the same way. It's just a matter of how many sign bits do you, I mean, how many exponent bits do you want, and how many mantissa bits that you want in the number that you're trying to represent. The way it works are the same. Then let's transition into today's topic, and should be pretty short if so that we have more time for the, as we said, the more like a live demo, but now it's driven by you. Operation in binary, right? So how do we add two binary number? The most obvious way you can do is to convert that to decimal and add them together and convert it back to binary, right? And this is going to be annoying and slow. So let me ask you this. Let's say we have two numbers, 123 and 987. How do I add these two numbers? So you just add each digit, right? You add each digit individually. So 7 plus 3 is 0, and then you add one carry over here is 1, plus one carry is 1. So it's 1110, right? So you might be wondering, why do I go back to a primary school topic, right? Because we want to figure out, well, can we do the same trick with a binary number? But before we go there, let me actually break this down and show why we can add the number this way, right? What is 123? 123 is 1 multiplied by 10 to the 2 plus 2 multiplied by 10 to the 1 plus 3 multiplied by 10 to the 0, right? With me so far? 987 is 9 multiplied by 10 to the 2 plus 8 multiplied by 10 to the 1 plus 7 multiplied by 10 to the 0. And I want to add these two numbers together. So one thing I can do is I can build a parenthesis this way, right? This works because I can shift where the add is in this equation, and I can group them together. So that way, I can just add 3 and 7 to get 10 multiplied by 10 to the 0, 10 multiplied by 10 to the 1, and 10 multiplied by 10 to the 2. And then you basically break this group and add them together so that we have the carry bit, etc., and we're done. So my question is, can we apply the same concept with binary number? The answer is yes, right? So let me have two binary number, 10101101. So how do I add these two numbers together? Well, this is basically 2 to the 6 plus 0 times 2 to the 2 to the 5 plus 1 times 2 to the 4 plus 0 times 2 to the 3 plus 1 times 2 to the 2 plus 1 times 2 to the 1, right? And you do the same thing. You see that this is basically 2 to the 6 plus 2 to the 5 plus 0 here plus 0 here plus 0 here plus 1 here. multiplied by 2 to 1, plus 1 multiplied by 2 to 0. So you can group it based on the digit again, right? Like this. And what you will get is, well, you just add digit by digit, right? 1 0 0 1 1 1 0 1, and that's the result, right? So that's how you can add two binary numbers together. All right, basic math, right? So let's go into more things. Can I use the same trick for subtract? Someone tell me that. Can I use this for subtraction? The answer is yes. I can subtract a number the same way, right? 101 minus 100. You subtract 1 here and nothing here. The same concept apply. Multiply also work the same way. You can group the digit together. So you have 101 multiplied by 110, right? This is 5. This is 6. When you just do this multiplication, 0 here, this is basically go back to like high school. I mean, not high school, like primary school, right? And then you 101. My bad. Let me erase this. So you first do the digit. Oh. Great question. What if you do A minus B where A is less than B? Wait a bit, because we're gonna cover that with Boolean algebra and tricks we can do with subtraction. All right, we will cover that in a bit. But you will do the same techniques if you do it by hand. So let me tell you. Okay, how do I do this by hand? Right? How do I subtract 5 with 6 by hand? How do I know that that's okay -1? So what if I have 0 minus 1, right? This is the same thing, A minus B, right? What you would do is you would have the borrow. You would borrow something that doesn't exist. You have the negative sign, and you borrow this becomes 2. So you know that this is -1, right? We can apply the same trick with a binary number. It works the same way as the decimal number. And hexadecimal also works the same way. For the multiply, right? You multiply 0 with 101, you get 0. You multiply 1 with 101, that's basically 101. And because you have the first digit 0, right? 1 with 101 again, so you have 20 first and 101. You add them together, you get 11111. This is so this multiplication is 30. So let's confirm that. 16 plus 8 plus 4 plus 2. And this is basically 30 as well, right? So this is basically how you can do arithmetic in binary. So let's go into Boolean algebra. Boolean algebra is not binary as arithmetic, but it's more like logical operation in binary. So here are the basics. Boolean algebra means that if I have the number 0, that's false, 1 is true. Are you all familiar with the concept of what we call a truth table? Anyone never heard about this before? Can someone tell me if you never heard about the truth table before? Because I'm gonna explain what it is. Otherwise, I'm gonna skip over the detailed explanation. All right, no one said anything. So let's assume that we know what is a truth table. It can be used to determine the result of logical clause, right? For example, I can say, if it rains today, there might be flooding. It's likely to be a true statement because if it rained today, if it rained, there might be flooding. The only thing that can be false in this statement is if it does rain, there's no flooding. But because I said there might be flooding, it means that, well, that's always going to be true, right? Might or might not. So the truth table is essentially a table that would list out the outcome of every single variable. So in this case, if I want to determine the result of A and B or C, the truth table would break down into, okay, A can be true, A can be false, B can be true and false, C can be true and false as well. And then you substitute A, B, and C inside this expression. So in this case, if A is true, B is true, C is true, that is going to be true. The second clause is also true. This will be true because C is true. If C is true, it's going to be true. This will be false because A and B, true and false, is false. False or false is false. False and true is false. False or true is true. This is false, this is true, and this is false. Right? So this is basically the result of A and B or C. Why do we care about the truth table? A few things. When you want to design the hardware, when you go down to the basic of the logic operation, remember that your transistor is really basic element. So you build from the AND gate, OR gate, and NOT gate. When you have that, these are your friends. You can build adders using things like this, using techniques like truth table, well, and more, right? But once you have the adder, you can add two numbers, then you can build math operations, and you can do multiply, you can do shift, you can subtract, right? And that's when the computer truly becomes powerful, because the basic elements is you can do and, or, and not. And with that, we can have the way to do Boolean algebra. The way Boolean algebra works is if I want to have the number, so if in C, right, in C, what will happen if I do 5 and 6? Anyone tried this before? Anyone tried this before? If you have not tried this, what is 5 in binary? Can someone type the binary representation of 5 on the chat? What's 5? 101. 6 is 110. What is 5 and 6 in this case? So the way this works is I would group the bits into the bit vector. In this case, 5 is 101. 6 is 110. Then I apply the operations bit by bit, which means that I would first AND this bit together. Then I'm going to AND this bit together, and then I'm going to AND this bit together. So 5 and 6 is what? What is 1 and 1? 1 and 1 is 1. How about 0 and 1? 0 and 1 is 0. 1 and 0 is 0. So 5 and 6 is 4. Yay, confusing, right? So bitwise operation, when you use Boolean algebra that has, for example, AND sign, or this is AND, or XOR, these will apply bit by bit by bit by bit. This is not, this is AND, this is OR, this is XOR, this is right shift, this is left shift. And these are different than logical operator. What is 5 and 6? 5 and 6 would evaluate to this. 5, this is true. 6 is true. So true and true is true, which in this case is the value 1. How about 0 and 6? It's going to be false, right? So this would result in the number 0 because 0 is false. Just note that this is different than logical operator. So one thing we can do, well, actually multiple things we can do. Now that we have the logical operator, we can play around with number. We can do multiple things, and one of the things you can do is to represent a set, anyone here, I assume everyone is familiar with the concept of a mathematical set, right? A set can contain object, and the object in there, as long as it's no repeated elements, it's a part of the set. You can use bit vector to represent the set operation. So the way I would represent the numbers, let's say my set can have the number from 0 to 7. It can be having the number from 0 to 7. So that way I will have the variable A that has 8 bits and B that has 8 bits. And let's say A is 1 1 0 0 0 0 1 1. This means that the set A represent is 0, 1, 6, and 7. Because this is the 0 bit, first bit, second bit, third bit, fourth bit, fifth bit, sixth bit, and seventh bit. When the bit has the value 1, means that number is present. So in this case, 7 and 6 is 1, means that I have in my set the number 6 and number 7. Bit for 1 and 0 also present, which means that I have the number 0 and 1 in my set. So let's say B also have 0 1 0 0 0 0 0 1. This means that my set is 0 and 6. So I can use AND for intersection. In this case, A and B is going to result in 0 1 0 0 0 1, which is the set 0 and 6, because if you intersect set A and B, you're going to get basically 0 and 6. Union, if A or B is basically a union operation, you're going to get 1 1 0 0 0 1 1, which is the set 0 1 6 and 7. XOR will be a symmetric difference. Symmetric difference basically detect what are the unique elements of A and B. In this case, A XOR B is going to result in 1 0 0 0 0, which means 7 and 1, right? Negation is a complement, basically would flip things that doesn't appear in my set would appear, things that has the number in my set would be gone. So this technique is used quite a bit in set operation. In set operation, you can represent set using a bit vector, and you can apply and or not XOR to this operation. So that operation on a set, which typically is costly, can be done in once. Actually, these are really, really quick. Typically a few clock cycle. Right? These are really, really, really fast operation. You can also do logarithmic, non-logical. You can do logical shifting by doing this n, this, right? And there's also another version called arithmetic shift. The difference is, let's say you have a negative number like negative 5, right? Arithmetic would preserve the most significant bit, while the logical shift would not. Right? So in this case, let's say I have a number that looks like this, and I want to shift right by 2, and this is the logical shift. When I do this, I will get 0 0 1 1 0 0 0, right? You notice that the sign bit is gone. But for the arithmetic shift, this same number 1 1 0 0 0 1 1 shift right by 2, it would preserve the ones, the sign bit. So the way this is done is you push everything to the right, right? You push everything to the right, but you preserve 1. So every time you push to the right, you add the number 1. So notice here that the sign bit is still there. So this kind of depend on what's the assumption of the GCC compiler, as well as like in Java, in Python, when you use shift, is it logical or is it arithmetic? Because it can change the sign for your number that you're dealing with. All right, so now you know some basic Boolean algebra and logical operations. What can we do? Can we do some trick to make your program faster? The answer is yes, we can have more complex operations. This is the beginning of assignment 3. Right? Assignment 3 will ask you to do tricks with the number using AND, OR, XOR, shifting, and logical operation like NOT to do fancy tricks with your number that you have coming in as an input. So negation is the simplest. If I want to compute negative n, this is basically not s and not n plus 1, right? Not n plus 1. Basically, negative 5 is not a 5 plus 1. So let's test this. What is 5 in binary? You have this on the chat already. It's 101, right? So let's say this is a 1 byte integer. So it takes only 8 bits. What is the result of me not this whole thing? So this equals 5. So not 5 is what? Can someone type in the number in binary was not of 5? So this part becomes 0, 1, 0, right? What else? All the 0 becomes 1, right? So it is basically 1, 1, 1, 1, 1. Let's convert that to a decimal number. This is negative 2 to the 7 plus 2 to the 6 plus 2 to the 5 plus 2 to the 4 plus 2 to the 3 plus 2 to the 1. Negative 128 plus 64 plus 32 plus 16 plus 8 plus 2. What's the value here? If you do this equation, you will get that this is negative 6. So not 5 is negative 6. Not 5 plus 1 is what? What's not 5 plus 1? If not of 5 is negative 6, what is not 5 plus 1? Negative 6 plus 1. So what's that value? Sorry if this is confusing. Let me know if this is confusing so we can repeat this again. Negative 5, right? So you can know that negative n is basically not n plus 1. And you might be wondering, why does this work, right? Why does this work? The reason why this works is when you not some number, right? When you not some number in the two complements format, you are basically add the negative maximum of that number, and you add the summation of any bits that were 0. So the difference always in the two complement format. So this format, you will see is guaranteed that if you not a number n, you will basically ended up having negative n minus 1 as a result. So to get negative n, you can do not n plus 1, right? So negation, negative n is not n plus 1. What does this mean? It means that if I want to add two number, right, I can add the two number, but the sign addition, well, this is the same. Basically, you can convert to unsigned and do a plus b and convert back to sign. It would work. The true sum, basically, when someone refer to true sum is if you have overflow bit, you keep that, and many modern processor can come up with a way to keep this overflow bit. So if you add the two numbers go over the maximum, there are ways to handle that. What about subtraction? We know how to add, we know how to compute negative n. So can I do a minus b? If I know how to add, and if I know how to flip the sign from n to negative n, so what's a minus b? It's a plus minus b, right? So what's minus b? If I don't know how to subtract, but I have the NOT gate and I know how to add, what can I do? This is the same as a plus not b plus 1, right? A plus not b plus 1. So this way, you can build a method to subtract using adder, right? So in your CPU, you just have a bunch of the unit that can add numbers. If you want to subtract things, not b plus 1 is your friend, and you put that into the adder. So that way you can quickly subtract. So hopefully that answered the question back then, like back about half an hour ago. Is what about if you have to subtract two binary number? In the computer, this is how it's done. You do a plus negate b minus 1. Multiplication by power of 2, something like 2 to the n multiplied by m. This can be done easily with left shifting. Why is that the case? Because let's say I have 5, right? And I want to multiply by 4. This is basically 5 multiplied by 2 to the 2, and that's going to equal to 5 multiplied, shift left by 2. So let me ask you this question. What is 3 multiplied by 8? Can I do this with shifting? Can someone tell me what's 3 multiplied by 8? Using shifting. This is 3 left shift by 3, right? And why does this work? Every time you left shift by 1, what do you do to the number? So every time you left shift by 1, right? Let's say you have this binary value and you left shift by 1, which means you add, right? Basically, when you left shift by 1, you add one more 0 here. Adding one more 0 means that I'm multiplying every digit here by 2, right? Every digit. Which means that you have the old, so this is, let's say this is n. Basically, the result of this left shift by 1 is basically it's n and the whole thing multiplied by 2. So every time you left shift by 1, it means that you're multiplying that number by 2. If you left shift by 3, it means that you multiply by 2 3 times, right? The same concept works for division as well. So if you have unsigned number, right shift, right, n, right shift by 2. This is basically n divided by 2 to the 2. N right shift by 3. This is basically the same as n divided by 2 to the 3. So we can use these techniques, and actually this technique is applied a lot in compiler and in the way to optimize your code to basically quickly compute division by 2 to the something, right? You can, another note on multiplication is when you multiply 2 n bits number, it is going to produce 2 n bits. So overflow can happen easily. So be mindful about the data size when you have to multiply a lot of numbers together. Because when it go over the limit, if you have a 32 bits representation, If you go over 32 bits, that number get cut. That number get cut. And you can do this with basically, when you know this binary number, you can perform what we call bit manipulation. And believe it or not, anyone hear about this concept of like Turing complete computer? Basically, it's a computer that can perform computation, all computation that's known. If you have the ability to and or and not and or and not, you can build a Turing complete computer just based on these three things. Based on these three things. What else? It turns out that the only thing you need in a computer is either NAND or NOR. NAND is not and, NOR is not or. Because with one of this, yes, the game is yes, exactly. When you have not and not or, you can build and or and not. So if you somehow can zoom into your computer and look at the CPU, and look at all the elements in there, you will see that it's just a bunch of these NAND gates. It's a NAND operation that put together and becomes a powerful machine that can do power of 2, adding two numbers, multiply, subtract. It's just a bunch of these NAND gates. All right. So what does this mean? Also in C, you can also convert complex operations and use, instead of looping around and do certain things, you can use bit operations. And we will do this in assignment 3. We will do these tricks in assignment 3. These tricks are pretty common actually when you have limited resources. Sometimes when you have to program in a microcontroller, you might have to rely on these tricks so that you use all the resources in the most efficient way possible, and so that it's still fast, right? One example is, let's say I have an array of integer, right? And each integer would have its pair, something like this. I have an array as 1, 2, 1, 5, 2, 10, 5, right? Every number here except for the number 10 has its pair. You have 1 right here, 2 right here, 5 has its pair right here. How can I quickly identify that one single number? So I'll leave it at that. Next week, after we're done with the quiz, we will come back to this and I'll tell you what's the easiest way. If you're in an algorithm class, you might have heard about big O notation. That's a linear time method to get this number. So hustle for you, right? Check it out. How can I use logical operations that identify that one number that doesn't have a pair? So last thing before we leave today, right? We will do a live coding exercise, but this is going to be driven by you. This is going to be driven by you. So before we go through the detail, let me stop the recording. So the file is not too big.